Rocks classification. Ingenious. They are formed by the solidification of magma. Sedimentary. They are formed from sediments. Metamorphic. They are formed from other rocks subject to high pressures and temperatures without melting. Rock properties. Porosity. Porosity is defined as a percentage or fraction of void to the bulk volume of the rock. Measurements of porosity are either done in the laboratory on core samples whereby actual conditions are simulated as closely as possible prior to measurement, or in situ via suites of electric logs such as neutron density and sonic logs. Permeability. Permeability is a measure of the ease with which fluid flows through a porous rock and is a function of the degree of interconnection between the pores. Permeability is a measure in Darcy units of, or more commonly, mil-Darcy. The apparent permeability is dependent on the type of fluid flowing through the rock, and this plays an important part in the interpretation of different hydrocarbon-bearing reservoirs. Wearing. The adhesive force determines which fluid will preferentially wet a solid. The tendency of one fluid to displace another from a solid surface is determined by the relative wearability of the fluids to the solid. Capillarity. In the reservoir, although the pore space do not form the uniform capillarity tubes, they do interconnect to form a complex capillary system which in turn gives rise to capillary forces. These forces can be measured under laboratory conditions for a given rock, fluids system, and in turn the capillary height can be calculated if the density forces of the fluid system is known. Residual oil. Water tends to displace oil in a piston-like fashion, moving first close to the rock surface where it is and aided by capillary forces in squeezing oil from the smaller channels. Residual oil is left in the smaller channels when interfacial tension causes the thread of oil to break, leaving behind small globules of oil. Coring. One way to get more delayed samples of a formation is by coring, where formation sample is drilled out by means of a special bit. The sample can be provided. Detailed geological description, porosity, permeability, fluid saturation, and grain density. These parameters are measured in the laboratory and serve as a basis for calibrating the response of the porosity logging tools and to establish a porosity permeability relationship. Core analysis. Core analysis can be divided into categories: conventional core analysis, spatial core analysis. Conventional core analysis: the core is usually labeled cut lengthwise to make the structure visible. Provides information on geology, residual fluid saturation, ambient porosity, ambient gas permeability, and grain density. Core analysis. Spatial core analysis provides the following information: porosity and permeability at elevated confining stress, electrical properties such as a formation factor and resistivity index, capillary pressure, wearability and relative permeability, mechanical rock properties such as compressibility, water fluid sensitivity for injectivity and well performance. Fluid properties. Naturally occurring petroleum accumulations are made up of large number of organic compounds, primarily hydrocarbons. Reasons to examine the reservoir fluids. A. A chemical engineer may be interested in a crude oil's compositions as to the amount of conventional products the oil will yield after refining. B. An exploration might have an interest in an oil or water compositions as is the sheets light on the origin, maturation, and degradation of the oil for geological interpretation. C. The petroleum engineer is particularly concerned to determine their behavior under varying conditions of pressures and temperature that occur in the reservoir and piping system during the production process. Products from petroleum. The distillation of crude oil results in various fractions which boil at different temperatures. If the residue which remains after distillation is a wax-like solid consisting of largely of paraffin hydrocarbons, the crude is designated as paraffin base. If the resin is a black, pitch-like solid, the crude is called asphalt base. Requirements to study the reservoir fluid behavior. Reservoir fluid and generally complex mixture of hydrocarbon exist as liquid-gas system under high pressures and temperatures. An important aspect of petroleum engineering is predicting the future behavior of a petroleum reservoir when it is put on production. Therefore, it is necessary to know the behavior of reservoir fluids as a function of temperature and pressure. To understand the behavior of complex systems existing in petroleum reservoirs, the derivation from ideal behavior are used. Phase behavior of hydrocarbon system. A phase is a definite portion of a system which is homogeneous throughout and can be separated from other phases by distinct boundaries. Solids, liquids, and gases are phases of matter which can occur, depending on pressure and temperature. Commonly, two or three different fluid phases exist together in a reservoir. Any analysis of reservoir fluid depends on the relationship between pressure, volume, and temperature of the fluids, commonly referred to as the PTB relationship. Single component system. Single component hydrocarbons are not found in nature. However, it is beneficial to observe the behavior of a pure hydrocarbon under varying pressure and temperature to gain insight to more complex systems.